All right, here we go. So let's begin. The first couple slides are going to be mainly for first class. We did already talk about rate of change in that class, but we didn't go through a problem. So just to clarify what rate of change is, remember rate of change is the change in one variable compared to the change in another variable. Okay, that is usually either positive or negative depending on the values you get. Okay, so and that could be, you know, cost over time. It could be S, which it could be, well, I don't know, whatever, but over time as well. That's how it changes. Now we find the derivative of a function, then we are able to actually figure out the rate of change of a cost function or something of that sort. I almost forgot. I forgot to delete all this. Did I don't think I got to this one, did I? Okay, so we had a couple slides different. That's right. So the volume of a hot air balloon after T minutes is given by the volume in meters cubed. Okay, and that is V equals T squared minus 3T, or T cubed minus, I did this last class, I think. 2T cubed minus 3T squared plus 10T plus 2, and we have an interval of 0 and 8 minutes. Okay, so just to clarify, we are taking a look at time and volume. So really we could actually write this as V of T equals that value. Something to consider. Let me change the font. I know it's dark. So we have this happening now. It says find the initial volume of the air in the balloon. That is when T equals 0 is the initial volume, which is 2. So very little amount, 2. Now, after 8 minutes, we have a larger amount, a much larger amount, and that larger amount would be plugging in the value of T equal to 8. And so if we plugged in T equals to 8, then we would get, and I'll go ahead and save you guys a little bit of time in the calculations, but you plug in 8 for each one of those, and you end up getting what was it, 913 point, 914 was it? Really? Are you sure on that? Okay, 914. Yep, 914. Now the real question that you are probably going to get is the rate of it increasing at 4 minutes. So here it is. It's gone up 1,000 roughly after 8 minutes. It's increased, and we want to figure out what is the rate of increase actually, what's the slope at that point. What is that slope? And so we have to think about what that slope is. Okay, at 4 seconds. So to do that, we have to find the derivative, V prime of T, and that equals, well, it was 6T squared minus 6T plus 10, I believe. That is V prime. It's also considered equal to dV over dt. I didn't write that in the last class. Okay? Okay, so that's the rate of change, but we're talking about 4 minutes. So what would our rate be? Well, it's equal to 6 times 4 squared minus 6 times 4 plus 10. And so we get about, it looks like 82 meters cubed. And now since this is a rate that we're looking for, it is volume over time, so over minutes. So 32 cubic meters per minute is the rate that it's increasing. Yeah?
So for A, when we find the initial volume of the air balloon at when T equals 0, would that just be 2?
Yeah, did I not write that? Okay.
No.
Sorry, I plugged it in, so we get V equals 2 meters cubed. Thanks for speaking up, too. This one we get V equals that value. stuff should be pretty straightforward. Okay, any other questions? No? Moving on. Cost function. So cost functions, now this got a little convoluted, but basically a cost function tells you how much something costs. A profit something, or a revenue function tells you how much you get. And then a profit function tells you how much you actually made. Okay? Revenue is incoming value, cost is outgoing value, profit is the difference of those two. And you definitely want to make a profit. Okay? Otherwise, you're basically not doing very well. So that's what this whole little shenanigan says right here. It's basically confusing, but all it's saying is profit equals revenue minus cost. That's what it's trying to say. So if I say, hey, what is the P prime? That would be the rate in which the profit is increasing or decreasing with respect to the number of items sold. So the problem that we're actually going to get to is right here. Oh, crud apples. And there we go.
How do you know it's recording?
Because I pressed record.
Okay.
All right, so the cost of labor, if you're ever interested in this, this is from economics, is usually the two first values. The cost of raw materials is the last, and then the fixed value, which is called overhead, is our last value. That overhead is usually fixed. Cost of labor is changing per hour or per unit, and the raw materials changes exactly per unit. Okay? So finding C prime, pretty straightforward. We just do the exact same thing. C prime of x, oh, we got that red again, darn it. C prime of x is equal to 0.000, and then we're take the 3 and multiply it here, so we have actually 39x to the second plus this times 2 is 0.004x plus 5. Now it says find the cost of 150. So we plug that value in, and I'm sure you guys can all put that into your graphing calculator. Am I right? Not if you're, otherwise I'll, good? Okay, so we end up getting a nice value. I believe it's 14.375. Is that right? 375? So what does that mean? That means the instantaneous rate of change when we're talking about 150 units. Okay? So we are talking about dc over dx. So it would be the cost per unit. The cost per unit. Okay? So now, if we do it the long way, where we actually plug it into the values, what we're doing here is we're finding one point and comparing it to another point. And the change in those points we can find by subtracting, and we end up getting about, I think it's 14.4. And that would be cost per unit. Okay? 14.4. Does that make sense? So this is the non-calculus way. This is the calculus way. Okay? Yes?
So to find that, we would just have to plug in 151 for that equation.
Yep.
And then 150 for that same equation, and then subtract the answers.
Yep.
Okay.
That's exactly right.
What was the calculus way, and what was the non-calculus?
Calculus way is using the derivative.
Okay.
Non-calculus is finding one point, finding another point that's one directly underneath it, and seeing how much it changed. Right? Let's say I'm making my 150th one, and it cost me, you know, total like $50. Next one, it's like $64.40. The difference is, 14.4 units. That's the overall cost per unit. Okay? You subtract that from the revenue function, and then you'll get how much you're actually making per unit. Okay? So let's say, that's nice. Let's say we're doing, we're selling it for $15 a unit, then we're only making 60 cents. If we don't do the math correctly, that's 4 cents, 3 cents difference, 2.5 cents difference. Now that doesn't make a big deal, but if we were to take this up to, instead of 150 to 150,000, then we're talking about a large chunk of money. So having that unit cost and getting the instantaneous rate is actually really beneficial to cost projections. Optimization. Now let's talk about optimization. So there are many problems in which we need to find the maximum and minimum value for a function. The solution is referred to the optimum solution, and the process is called optimization with an S. Optimization with an S is the British way of doing it. Okay? Note that it is essential to also examine the values of the function at the endpoints of a domain for global max and min. So this is finding that value. Now, this right here, really, you're not going to relate. Oh, that's great. You're really going to find a specific example for optimization. You're really never going to see this little curve here, the optimizing curve. What we are going to look at is, hey, here's a volume, here's a, let's say a circumference. No, not circumference, that's easy. Here's a volume, here's a surface area. We're going to find the optimum volume that we could have for that surface area. That's one of the big things that we're going to do. Okay? So optimum solutions are the same thing that we do. Okay? Optimum solutions, we're looking for the point in which it changes. And so what we can do is set it equal to 0 to figure out where the maximum volume is or the minimum volume is. Sometimes we want to minimize volume. Okay? Sometimes we want to maximize the volume. Okay? You have to have a certain amount of surface area, and you want to keep that cat inside the box and uncomfortable. So, I'm just joking. But
The poor kitty.
yeah, the poor kitty. So you want to keep it, maybe you want to like create a box that you only have like 25 square feet of material, and you want to create a box that is the largest possible volume. How do you do that? Well, you can use calculus. All right, so optimization has a 4-step process. First thing, and I am going to tell you, it is necessary to do this. Draw a large, clear diagram. I know it sounds like I'm encouraging you to do art, but that is true. I am encouraging you to do some art, okay? You're looking for a box, draw a flipping box, okay? Do it. It helps. I know it does help, okay? Sometimes it's a cylinder. On your IAs, it was, hey, take that cylinder, take a can, take this cup right here, and I want you have 12 feet squared of material. I want you to make a cup, something like that. I want you to optimize it. Optimize that cup space. That's a big cup. So
How big do you think it would be?
I don't know. Doesn't matter. Step 2. We're going to construct a formula with the variables to be optimized. The formulas they're not given to you. It is not a given formula situation. Okay? What you are given is usually an overall value, like a 4-liter container, 3,500 square feet, that kind of stuff. Okay? So what we are going to do is construct some sort of formula that can be optimized. as the subject. It should be written in terms of a single variable such as x. You should write down what restrictions there are also. Like, can you have negative volume? No. Can you have zero volume? Yeah, but that's not an optimization, obviously. If you had zero volume, what would the surface area be?
0.
Zero. It wouldn't even exist. Okay? So we kind of stay away from zero and negative.
So it's basically undefined.
Well, no, it just doesn't exist. Like, there's no such thing as it.
Okay.
That's like, it's like the tooth fairy. Sorry, guys. Doesn't exist. There's no point in thinking about it. It's not like, it's undefined, it's just, it doesn't exist. So, you should write down what restrictions there are, which is in intervals. After you do that, that's the hardest part, I think. After you do that, you find the first derivative, and I say first derivative because you can find multiple derivatives, but you find the first derivative of it, and find the value of x where it is 0. This is an important step. You are finding the critical values. Okay? You set your stuff equal to 0. You've done it before. If there is a restriction to the domain, such as a is less than or equal to x, which is less than or equal to b, the maximum or minimum may occur either inside those two restrictions or at those restrictions. Okay? May occur either when the derivative is 0 or else the endpoints. Therefore, you need to look at f prime of a and f prime of b, show using the sign diagram or the graphical test that you have a maximum or minimum at those critical values. Let's do an example. Okay, a 4-liter container must have a square base, vertical sides, and an open top. Who's that? Shh. Freaking, can someone just...
She's
not
left.
there. She left. She's left a while ago.
It's okay, just leave it. Okay, 4-liter container. Find the most economical shape for which minimizes the surface area of the materials needed. So we have a specific volume, but now we want to say, hey, my company wants to create something that uses the least amount of material, which means least amount of surface area. And to do that is a little step. So first off, I'm going to take this 4 liters and I'm going to convert it. Now there's a conversion chart that you're going to be given. So 4 liters, or 1 liter, 1 liter is equal to 1,000 centimeters cubed. It's one of those beautiful things that happens. Okay? Another thing we need to know is what volume equals. What's volume of a cube? Or of a rectangular prism?
Height times width.
Yeah, length times width times height. Okay, but it's giving you actually some information here. Okay, and if you're wondering, it's actually right above Parker. Harrison, dang it. But still. Okay, it's right above there. It says cube, same kind of thing, length times width times height. Okay? So, what does that mean? Now, first off, let's get some information here. Square base. Interesting, it's a square base. Oh, wait. Before that, surface area. We got to deal with surface area. Surface area is equal to thanks. Is equal to all of the I always say thanks to him. I always say thanks to him.
Janitor.
I know, he hasn't vacuumed in here for a while.
Oh.
Anyway, it's a square base. Okay, so we have x, and if that's x, what is this side? Also x. So we'll call this other side y. Okay, so now we need to figure out the surface area. The two bases. Well, what's one base equal to? What is this base equal to?
X squared.
X squared. And how many are there? there's only one, oh, at the top's open. Yes, there's only one value. So that's x squared. If the top was closed, it would be 2x squared. Okay? What about this side? What does that side equal to?
That's one.
X times y. And how many of those are there?
4.
There's 4. So we say plus 4xy. Now here's an issue we have. We're trying to optimize surface area, but it says, if you remember, that we need to have one variable, a single variable here. Okay? So what I'm going to do is I'm going to use my volume to solve for y. You have to use a separate equation to solve for y. So here's what I'm going to do. I'm going to say volume equals, because we're given the volume, 4 liters, volume equals length, which is x, times width, which is also x, so we'll square it, times y. What is the volume equal to, though?
On one of the sides. No.
Volume is everything that fits in this container. How much can fit in that container? 4 liters or 4,000 centimeters cubed. So we're going to go 4,000 equals x squared y. Now from this, we want to get y by itself. Because if we get y by itself, we can substitute it in for surface area. So I'm going to divide by x squared on both sides. What does that mean? That means y equals 4,000 over x squared. And I'm going to take that value and I'm going to put this directly in for that. So I'm going to say, instead of surface area SA, I'm going to call it S sub x now, because it is one variable. That is going to equal x squared plus 4x times 4,000 over x squared.
So that eventually equals 16,000.
Yep. I'm getting there. So we simplify this a little bit. That is x squared plus 16,000 over x. Or you could even write it like this, x to the negative first. Why would I do that? Because I'm going to optimize my volume. All right, so now I find S prime of x. S prime of x, we end up getting x, or sorry, 2x minus 1,600 x to the negative second power. All right. Okay, so far? Okay, so far so good. Now we still need to optimize that area. So we're looking at the critical value. And for this one, if we have a subtraction, we're talking about a graph that looks like this. It's going to start up here, it's going to dip, and then come back. So we're going to try to figure out what that point is. What's the slope at that point? The slope is 0. And this is the slope equation. That's good. So that means we set it equal to 0 and solve for x. Okay? We're running out of space. I'm going to keep this. I'm just going to... That didn't work out at all. Cool. Now I'm crashing it. Don't crash. Oh, thank God. Just leave it, Andrew. All right, all right. Okay, so let's do that over here. Oh, shoot, wrong button. Let's do it in white. So we go 0 equals 2x minus 16,000 over x squared. Okay? Now you might be thinking, holy Moses, that x squared on the bottom, that's no fun. Don't worry about it. Forget about it. Check this out. Add that over. Add 16,000 over x squared over to the other side. We get 16,000 over x squared equals 2x. Can we get rid of this x squared on the bottom? How do we do that? Multiply by, there you go, multiply both sides by x squared. Multiply this by x squared and this by x squared. So we get 16,000 equals 2x to the third power. Divided by 2, we get 8,000 x to the third. And then we do the cube root of that value. The cube root of, let's see, of
8,000.
8,000, why am I just brain farting, equals x, which is 20?
Yeah.
20. Okay. So x is 20. Woo! X is 20. We can figure out finally y by plugging it back into the original equation. Right here. Okay? So x equals 20. We found one of the optimum lengths. Does it say find the most economical shape to minimize the surface area? We found x equals 20. Now this, because we cubed root it, it's only centimeters. Because remember it was centimeters cubed. So now it's just centimeters. So we go back to the y value. So I'm going to go back to, actually, why not this? 4,000 over x squared equals y. 4,000 over 20 squared equals y. That is 10 equals y, isn't it? So y equals 10 centimeters. I don't know why you guys all sit in the back and over there. You can never see. You should sit like over there. You have to look right through me.
It's like a fraud reflector. It's really the best. You can't see.
I don't know. Anyway, that is a great problem. That is a problem that you will see. Okay? Any questions, comments, concerns? Well, just questions or comments, please.
So that's it.
So thumbs up. Is that it? No, we got other ones. Yes.
Well, no.
What is this 10? So we've just created a square-shaped box that now our sides are 10, 20, and 20. That's the optimum surface area. What is that surface area? Well, you'd have to plug it in right here to figure out what the surface area is, but that's a good question. Okay, it says what is the most economical shape which minimizes the surface area of the material needed. I guess we would plug the values in and figure it out, which is 20 squared plus 4 times 20 times 10. I don't think I actually do that. I don't get a value here, so if you wanted to...
Find the most economical shape, so you just need to put it in.
Yeah. Which minimizes the surface area of material. So anyway, that's how you do it. All right. You want to try one of these on your own?
Yeah, but the next one is this.
Yeah.
Is it this one?
No. This is different. Okay? It's a little different. All right. So, This is another great example of a IB question that will show up for sure. Okay? A square sheet of metal, 12 centimeters by 12 centimeters, has smaller squares cut in the corners as shown. And if you think about it, what's going to happen is you're going to take this little box here and you're going to fold up those corners to make some sort of box shape. Okay, but the question really is, I want to maximize the volume that I get. I'm going to take them and fold them up. Okay, so these are cut. Now, when they do this kind of problem, where is the missing value? Well, we don't know how much was cut, but we do know that they're equal. Every single one is cut equally. So let's keep reading the question. What sized square should be cut out so that when the sheet is bent into an open box, it holds the maximum amount of liquid? Okay? Or whatever. And why liquid? Why can't it be like solid? Cheese? Whatever. So we're going to take these and we're going to see what this x value is when we fold it. This is a pretty good drawing, actually. Really get an idea, right? Yeah, it's really great. To the point where we get a box that has an open top to it. Okay? So we're trying to figure out what those x's are. X, x, stuff like that. Okay, so let's start with the volume. Okay? What is the volume of this particular figure? Well, we're going to maximize the volume, so we got to think about this. Here's our box here that we have, and we have side lengths here, but are those side lengths, are they equal to 12? No, what are they actually equal to right here? Yeah, CV says 12 minus 2x right here. Okay, and he says that because, try to find a good color here. Because we have the distance from here to there as a side length, and the distance from here to there as a side length. But look, they're missing x. They're missing 2 x's. So the volume is going to equal 12 minus 2x. Okay? Now when we take the volume, we do length times width times height. What's height? X. Well, that's kind of nice. What's the length, though?
12 minus 2x.
It's also 12 minus 2x. Okay? If you want me to draw this out, here's what happens. We get this little box here. We have folded up the corners. Our height is x. We have 12 minus 2x right here and 12 minus 2x. There's my little diagram that I was going to draw. Okay, the diagrams help. All right? So length times width times height, we get this. And our volume equals 1440. Whoa, that's way too much. Minus 48x plus 4x squared. Oh, times x. So we end up getting v equals, let's go ahead and put it in order, 4x to the third minus 48x squared plus 144x. So that's our volume. But that is something that we can definitely optimize, correct? Yes. How? Finding v prime. If we find v prime, it is saying the volume optimized. The reason why we used volume on this one is because they gave us the volume. Okay? If they gave us what the surface area was, or one side, we wouldn't have any issues. But we have two variables here. We can't have two variables. This one we have only one variable, so we're good to go. We end up getting 12x to the second minus 96x plus 144. Now we want to optimize this, which means what? We want to find the maximum value. As you remember, we're starting with a small value. It's going to go up, and then it's going to eventually come down. Okay? That's what... God, that's so stupid. I hate that little dead spot. So we're trying to find that point right here. And what's the slope at that point? 0. So we're setting v prime equal to 0. 0 equals 12x squared minus 96x plus 144. All of those can be divided by 12. 0 equals x squared minus 8x plus 12. We factor this. 0 equals x minus 6, x minus 2. Yeah?
Wait, can you do it again, like how you know that it's moving, what you said?
So because we're trying to find the maximum value, then the slope of the tangent line through a maximum point is always 0. And so we set that slope equal to 0. Okay? So m equals 0 right there. So we end up getting two values. X can equal 2 and 6. Okay, it makes sense a little bit. It's what happens is it gets to 2. You get optimization. It passes. Well, now one of these actually doesn't make sense. Now think about it.
The 6 is already half of the box. And
Yeah.
so
6 is half of the box. So if this is 6, what's the other half?
6.
6, which makes the box non-existent. So only x equals 2 centimeters works.
So the 6 is extraneous then?
It is extraneous. That would be the correct word, yeah. It's just, you got to look at it in common sense terms. Doesn't make sense. You wouldn't have a box. Okay? Questions about that? Okie doke. Now we have one more that is fun, to say the least. This one is a really long question. So let's go ahead and take care of this one. The optimization using technology. Okay? If you do not know how to differentiate a function, we can use technology to find the optimum solution. In the following exercise, use the graphing package, oh, that's interesting, or your graphing utility to help you solve the problem. The distance formula from A to P is given by D equals the square root of all that jazz. Okay, so we're going to show, using a triangle PQA, how this formula was obtained. Interesting. Okay, I like that. That is basically saying, what is the value of this right here? Well, it is Pythagorean's theorem that you're going to want to use. Okay? You would do QA squared plus QP squared equal to PA squared. Plug in the values that you know. Well, the distance from here to there is looks like it's x. And the distance from here to the very end is 5. So QA is equal to 5 minus x squared. QP, same thing. From here to there, it looks like it's 1 unit. And from here to the top, it looks like it's y units. So that indicates that we'd have y minus 1. And then PA squared. PA squared is just D, I guess you could say, because we have D here. D squared. And so we end up getting the square root of 5 minus x squared plus y minus 1 squared equals D. All right, so that's that. Explain why D equals this. Well, D equals that because it makes sense, I guess. But if it's interesting that we could pick any value on this particular curve here, and that would be our solution, okay? Which is kind of interesting. What we want to do, however, is find the smallest value of D, smallest value of this distance, and the value of x where it occurs. Okay? So we want to optimize this distance and then figure out where that x is. Okay? And the last thing is interpret the results. Okay? So, a couple of things we need to do. We need to oh man, I don't know if I'm going to do this on one slide. Let's see, hold on a second. I don't think I did it right last time. That's awesome. Okay, so to find the smallest value of D, we would find the derivative of D and set it equal to 0. Okay? So the only problem is that this is one massive equation. Okay? Well, let me think. What we could do is find that point first. No, we can't do that. We don't know the slope. Because it would be a normal that we're looking for. Okay, I'll just go with what I had. D prime. D prime is going to be the chain rule. Okay, and that seems fine, dandy. So, oh, I missed this. Sketch the graph of D against X for 0 to 6. Missed that. Okay. So this is the same thing as 5 minus X squared plus Y minus 1 squared. And then we're going to have that to the 1/2. No, they wouldn't. They're not going to do this. They're not going to make you do this on a... This is not prime. They're not going to make you do this on an IB exam. What am I missing? I'm missing something here. Set them equal to each other. Yeah. Oh, God. Okay. So set them equal to each other? And we would get the point of intersection?
Well, we could find the slope with it though, because it wouldn't necessarily be a right angle, but it would. You could find the slope with the point of P to A in relation with X and Y.
Mm-hmm. All right, I'm gonna have to cheat on this one. I'm having a brain fart. That's why I like to prepare. Okay. I think what you do is you find the derivative, you plug it into your calculator, and you find the max or the min. That's what I'm pretty sure you do, but I'm not very happy with how difficult that is to find the derivative. So, where would I find that? Where'd I get this problem at anyway?
From the operators or sectors.
What if you got it from the textbook?
That's where I'm looking. Should be section.
The orange textbook.
Oh, I don't think I did. They don't have this kind of stuff.
Okay.
Rate of change. Organization. Oh, here it is. Okay. What do they have you do here? Using technology, the coordinates of the turning point are... You jerk.
What? You used to, well, how do you...
Okay. What does it say to do? It says...
Yes.
The shortest distance from A sub 5, comma 1... A, well, 5, comma 1 is the graph of... I have no idea what it's looking for us to do.
So should we just not do it then?
Well, I found it, the derivative. It turns out to be something really gnarly. Oh, great, I'm recording the screen here. Friggin'. Whoa.
This is going just like the room went.
This is not going very well. You get d prime equals to, this is crazy, but it's negative 2. It's a very complex type of problem here. Square root of x squared minus x to the fourth minus x squared minus 10x plus 26. That's what you end up getting.
I vote we never do that again.
Yes.
And I guess you would graph that and set it equal to 0 and you would get your values. Wow, that's really a poorly written problem. Way to go.
You were just like, don't do problems like that ever again.
Alright.
Like, is it on the IB test?
I don't think they'd ever do that.
I don't think they would do that. There's gotta be a better way to do
Everyone
it.
would just skip it.
Anyway.
They can do everything.
There's the derivative. It's nasty. And I'm pretty sure that this is to the...
They have that on there.
Shh! Guys, quiet please. This is to the third. Yeah, I don't think they're going to do that. It's going to be a better problem that you can do within a few seconds. Oops. Close. Save. Okay. So, we should know how to do this on using technology though, and there's a thing in your book that they tell you how to do this using technology, and it is right there. It is. So find all and classify stationary points. You plug this in to the equation. You plug that in, and all you have to do is you find the points where it crosses 0. Okay. So you have a couple of options. One, stationary points. You plug them in, and you plug in the original equation and find the max and min. Or 2, you plot the derivative and you find out where it crosses the x-axis. Okay. Well, that's what the graph looks like for the volume of that box here. I just am really not very happy with that one problem. You can probably guess.
Oh, Mario.
We're doing calculus.
Even he doesn't like calculus.
He doesn't like IB
You
cal.
scared him off.
He doesn't like the calculus version of IB. I gotta stop this. Stop. 50 minutes. Holy